Hello and welcome to the final film in a series of 3 about the high level equilibrium topic. Here we're going to be looking at things called ice tables, and these are a pretty cool way of helping ourselves decide the values that we're going to put into an equilibrium constant expression so that we can calculate an equilibrium constant using a mole ratio in an equilibrium equation. So you hopefully have seen the film about how we calculate equilibrium constants, right? These are a different type of problem now, because what we're often told is some information about some stuff that we started off with and some information about things that we end up with. The thing is, when you write an equilibrium constant expression, and remember that it's all about products over reactants, and although this equation looks similar to the ones we've studied up until now, you can see it's written the other way around. So we're now going to have H2 multiplied by I2 on the top of this fraction, okay, divided by HI squared. The concentrations that you enter into an equilibrium constant, perhaps unsurprisingly, are the concentrations at equilibrium, right? And notice here that although we've put 1 mole of hydrogen iodide into this container, it wasn't at equilibrium when we did that. In fact, we heated it and then later it reached equilibrium, and only when it reached equilibrium were there this many moles of iodine. Okay, so some of the hydrogen iodide turned into iodine. Clearly, there won't be the same amount of hydrogen iodide left at equilibrium, so we're going to have to figure out how much is there before we know all the values to plug into our equilibrium constant expression. Okay, so how are we going to do that? Well, guess what? We're going to use an ice table. Now, it's useful to understand why it's called an ice table before we start. So this I refers to initial values, so what we started off with. Okay, so this would be an initial value here. That's what we put into the container. There will be a change in the values, okay, before the system reaches equilibrium. And so what we're going to do with our ice table is we're going to see if we can figure out what the initial concentrations were, how much they changed by, and what their values were at equilibrium. Okay, so let's start off by thinking about how many moles of HI there were at the start. Well, there was 1 mole. Okay, but remember, we don't put moles into our equilibrium constant expression, we put concentrations in. So moles per dm cubed means we're dividing the moles by the dm cubed, so 1 over 20. Okay, what was the concentration of H2 initially? Well, it was 0 because there wasn't any put in there. What was the concentration of I2 initially? Also 0. What happened to the amounts of H2 and I2? Well, they must have increased because the HI would produce them. How much did they increase by? Well, we're only told directly about the number of moles of iodine. So we know that the change in the number of moles of iodine was 0.114 moles. We can see in this balanced equation here that the number of moles of hydrogen is the same as the number of moles of iodine, and so the number of moles of hydrogen must have changed by the same amount. Okay, so it changed by 0.114 moles. The number of moles of HI, or the change in the number of moles of HI, would have been twice as much as this, because there are 2 moles of HI in this equation for every 1 mole of the others. So in other words, the number of moles of HI changed by minus 0.228. So this is the number of moles that changed by that amount, not the concentration, right? But our equilibrium concentration would now be 1 minus 0.228 divided by 20, because the volume of the container hasn't changed, right? So this is going to be 0.772 divided by 20, and that equals 0.0386. The initial concentration of H2 was 0. The final concentration, well, it's gone up by 0.114, so the final concentration is 0.114 divided by the volume of the container, which is 20, and that equals 5.70 times 10 to the minus 3. And that's going to be the same for the I2 because it's in the same size container, and then there are the same number of moles of it. Okay, so we've now got the values that we need for our equilibrium constant expression, right? We've got, oops, shouldn't have done that one. Well, in fact, let me just scrub all of them out and move on to the next slide, because here what I've done is I've summarized those values which we've just found. Okay, here are our equilibrium concentrations of those three substances. So let's just write our equilibrium constant expression again. That's H2 multiplied by I2 divided by HI squared. And now that I've found all these concentrations, it's simply a matter of plugging them in. So this will be 5.70 times 10 to the minus 3, and that's going to be squared. And then we're going to divide that by 0.0386 squared. Okay, and if you do that on your calculator, I'm not going to do it in my head certainly, so I've done it on my calculator, and I found that that equals 0.0218. Okay, now the only thing that we've got left to do is to figure out what the units are going to be. There are two concentrations on top, two concentrations basically on the bottom because it's squared, so this has no units. And you might be thinking, well, hang on a minute, the equilibrium constant for this reaction before was 46, and now it's not. Well, remember, this is now this reaction written in reverse, so the equilibrium constant is upside down, and you can see that that is not far off being 1 over 46, right? But bear in mind the temperature is slightly different, so it is going to have a slightly different value. Okay, these are an important problem to know how to do, because you get them in exams and they're worth quite a lot of marks because there's a lot of steps. Okay, so it's definitely something that is worth practicing. Okay, but if there's anything in this film that you wanted to comment or ask questions about, please feel free to come and see me or to post a comment on YouTube.